At the end of the last video, we sort of touched on a type of relation called equivalence relations. What we're going to do is review the definition of equivalence relations, which we actually gave in the last video, and then we're going to look at an example relation and prove that it is an equivalence relation. So remember, we had three important properties that made up the definition of equivalence relations. So if A is a set and R is a relation on the set A, we say that R is a reflexive relation if every element is related to itself. So A, R, A for all elements in A. We say that R is symmetric if whenever A is related to B, then B is related to A. And then we say that R is transitive if whenever we have both A related to B and B related to C, then A is related to C. And this leads to the definition of an equivalence relation. A relation on a set A is an equivalence relation precisely when it is reflexive, symmetric, and transitive. So let's go ahead and define a relation. So that we're going to call the relation E, and it's defined on the set of real numbers. And here's the definition. We say that x is related to y, so x e y, when x squared is equal to y squared. So when we square the two numbers, we get the same number. So we first look at the reflexive property. Now I should warn you that the reflexive property can actually be a little bit tricky in terms of a proof, because the thing to remember with a proof is that we always have to have something that we're assuming and something that we're trying to show. And often with a reflexive property, it's easy to get confused about what we are assuming. Well, remember, a reflexive property says that every element is related to itself. So we have to look at every element. So we're going to assume that we have an arbitrary element x that is a real number. So we assume we have an element of the set that we have the relation on. And then we want to show that that element x is related to itself. All right, so remember, the test for x being related to y is seeing whether or not x squared is equal to y squared. So if we want x to be related to x, we've got to see whether or not x squared equals x squared. Well, it's pretty clear that x squared equals x squared. They are literally the same number, and that tells us that x is related to x. So that's not so bad. Now, for the symmetric property, we're going to assume that x is related to y, and then we're going to show that y is related to x. So since we're assuming that x is related to y, we have that x squared is equal to y squared. But if x squared is equal to y squared, that means that y squared is equal to x squared. But if y squared is equal to x squared, that is exactly the definition of y being related to x. And finally, we look at the transitive property. We're going to assume that x is related to y and y is related to z, and then we're going to show that x is related to z. So we know x is related to y and y is related to z, and so it follows that x squared is equal to y squared and y squared is equal to z squared. Now, since x squared and z squared are both equal to y squared, that must mean they're equal to each other. So x squared is equal to z squared, which means that x is related to z. So that tells us that E, since it satisfies the reflexive, symmetric, and transitive properties, it must be an equivalence relation. Okay, so now I think you're ready to work on the activities in the PDF file called Equivalence Relations, and that is the link that's included with this video.